What if in 2026, astronomers finally detect something they've been searching for over 2 decades? A faint, rhythmic signal, hidden within the light of a distant star. Not a planet, but something smaller, orbiting a world far beyond our own. A moon, outside our solar system. If confirmed, it would be the first exomoon ever found. A discovery that could change how we understand the birth of planets, the balance of worlds, and the possibilities of life itself. When we talk about space exploration, planets often take the spotlight. But moons, the silent companions orbiting them, are just as important. Earth's moon, for example, does far more than light up our night sky. It stabilizes our planet's tilt, keeping our climate steady. It controls the tides, stirring the oceans and shaping the very chemistry that may have led to life. And beyond Earth, the solar system is filled with extraordinary moons, each one rewriting what we thought we knew about where life can exist. Europa, a moon of Jupiter, hides a vast ocean beneath its icy crust, an ocean containing more water than all of Earth's combined. Enceladus, circling Saturn, ejects towering geysers of water vapor and organic molecules into space, proof of activity deep below its frozen surface. And Titan, larger than the planet Mercury, has rivers and lakes made not of water but of liquid methane. These worlds show us one thing: life might not need a planet at all. A moon, with the right conditions, could be just as alive. Astronomers have chased exomoons for years. Two signals teased us: Kepler 1625b, and Kepler 1708b, tantalizing dips in starlight that might be moons. But evidence wrestled with uncertainty. Analyses argued both ways. The truth? We were right on the edge of what our instruments could see. If such a signal were confirmed, it would mark a new chapter in astronomy. For years, missions like Kepler and TESS have spotted thousands of planets, but no confirmed moons. Detecting one would mean our instruments are finally sensitive enough to see not just worlds, but their companions. Scientists would then begin studying how that moon formed. Did it take shape beside its planet, or was it once a wandering world captured by gravity? Step by step, we'd begin to understand if moons like this are common, and whether some could resemble the ocean worlds we already know in our own solar system. When astronomers finally think they've found an exomoon, they can't see it directly. It's far too small and faint. Instead, they detect it through the tiny effects it leaves in the starlight. If a planet passes in front of its star, the light dips slightly. That's a transit. But if the planet has a moon, that moon might cross a little earlier or later, creating an extra flicker before or after the planet's main dip. That's what we call transit choreography, the dance between planet and moon. Sometimes the moon's gravity causes the planet itself to arrive early or late during each orbit. These are the transit timing variations and transit duration variations, tiny shifts that reveal an unseen companion tugging on the planet. In rare cases, if the moon has an atmosphere and it also crosses the star, a fraction of starlight passes through it. Scientists can then study that faint fingerprint in the light spectrum to detect molecules, just like we analyze exoplanet atmospheres. If the first exomoon is ever found, it could fall into one of two likely types. It might be a giant moon, almost the size of Neptune, orbiting a massive planet many times larger than Jupiter. That kind of moon could be a captured world, once a small planet that drifted too close and was trapped by gravity. Cold, far from its star, it would reflect a faint blue light wrapped in frozen gases and thick haze. Or it could be a smaller, rocky moon, roughly Earth-sized, orbiting a gas giant that lies in the habitable zone, where temperatures allow liquid water. That one would have tides, seasons, and gentle illumination from both its star and its parent planet. Its skies might glow softly from reflected light, and beneath that, perhaps chemistry could begin, the quiet start of something living. Life doesn't require paradise, it requires gradients, places where energy and molecules meet and react. On an exomoon, you get tides, magnetic shielding from the planet, eclipses tempering surface conditions, and perhaps a subsurface ocean safe from radiation. If this exomoon lives in a habitable zone system, tides and gentle starlight collaborate. By late 2025, NASA's official exoplanet count crossed 6,000 confirmed, with thousands more candidates waiting in the queue. That's not a catalog, it's a preface. If even a fraction of giant planets host moons, and a fraction of those are big or warm enough, then the cosmic census of possible habitats explodes. If one exomoon is confirmed, that discovery will only open the door wider. Telescopes like Webb would study its light in detail, searching for signs of atmosphere or oceans. New observatories, including Roman and next-generation ground telescopes, would turn their gaze to other stars, refining the techniques that made the first one visible. With every new detection, the search would grow faster, sharper, and soon, finding moons beyond our solar system could become routine. If this discovery happens, it won't just confirm a moon around another world. It will prove how far our technology, patience, and curiosity have come. Each small flicker of light brings us closer to understanding the systems beyond our sun. The search never really ends. It only gets clearer. One day, a distant star's light may flicker twice, first from a planet, then from its moon. That single moment could change how we see the universe, not as a sky of lonely worlds, but as systems filled with companions, oceans, and endless possibilities. Somewhere out there, under another sun, a moon may already be waiting for us to notice its faint reflection.